Hello, everyone. I'm Geoffrey Spigoulet, and I work as a consultant at the machine learning team. And currently, I'm working on multilingual translation systems. And in this presentation, I'm going to talk about this, and as well as transformers. And at the end, if I have some time, I will talk about the potential way to understand a sperm whale's communication system as well. So first, I want to give you a brief introduction to transformers. Transformers were like introduced in 2017 in a famous paper called "Attention is All You Need," and basically this is the architecture. I definitely won't go into all the details here, but I want to give you an overview how the transformer works. So there is an initial input embedding on the input sequence. In this case, it would be like I'm a student as in French, and you would tokenize the sentence into a bunch of tokens. Here, each token is it's a word, but it could be also a support tokenization, as we will see later. And then these tokens from the vocabulary are projected into vectors with a certain dimension, which are these embeddings here, and then a way to incorporate information on the position of each token in the sequence. And in the original paper, they used a bunch of cosines and sines functions in order to encapsulate these, in order that the model can learn the position of each token. At the core of the transformer model, there is the attention mechanism, the so-called multi-head attention, which is a bunch of matrix multiplications, a scaled product. But the intuition behind the multi-head attention is that each token or each word in the sentence is paying attention to itself and to other words and learns to understand some context. In this case, multi-headed because there are like several heads that would focus on different features of the sentence. We can see here the head labeled in orange is from the word eat. It's focusing on the animal, and it's a bit complex here to see all the different heads. But the idea behind is that you would have this way of representing the input as these vectors, and then multiplying with different matrices that are an abstraction of queries, key, and values. With these matrices are going to be learned during the training of the model, and the resulting matrices are going to be multiplied the so-called scale dot product attention, which is the queries matrix multiplied by the transpose of keys matrix divided by this scaling could be another a different number, but in the original paper they use it the square root of the dimensions of these matrices, which is I think it's 64, which is smaller than typically than the original embedding vectors, which are around like 500 or 1024 sometimes, depending on the model. In the same process is done in parallel with each of the different heads, and the resulting matrices are concatenated and then multiplied by a weight matrix will result in a matrix with the same with initial dimensions that can then propagate into the next layer of the neural network. So from the first self-attention layer, then there's going to be a feed forward layer, and this will be the so-called encoder block. And there are like several of them concatenated, and finally on the right side we have the decoder block, which I think I will explain a bit more later. So that was the self-attention from the encoder block or encoder stack. And in the decoder, what we have is as well a self-attention, but that is masked in order to avoid. And just to put some context for training, we would use like a sentence in one language, and here in the output would be like another sentence of the translation of the translated sentence. And it so the idea is that during training we don't want the self-attention, the tokens, to pay attention to the tokens that are coming after, so into future positions. And we see another attention layer here, which is also called the cross attention layer, which has the matrices from the keys and values from the encoder block propagating into the decoder. And here, after the self-attention from the decoder block, there is the queries matrix, which are going to be combined into this cross attention layer. It might be a bit so I might go too fast on explaining all these details, but the core idea is that the transformers key ingredient here is the tension mechanism, and they are more powerful than other systems for sequence to sequence generation. For like they can be trained in parallel, and that allows parallelization during training. And then I haven't mentioned that there is also a residual connection and a normalization layer that also escapes that propagates into the encoder and the decoder. And at the end, there is a linear matrix that will project the outputs of the decoder into a long vector with the length of the number of tokens in the vocabulary, typically on the order of several thousand tokens, which might be thought as words, but as I mentioned, they can be supports. And finally, this vector that is also called logits is gonna have a softmax in order to make to generate all the probabilities that will be positive and adding up to 1. And the idea is that the token with the highest probability here, it's gonna pick up, it's gonna be taken into the next, it's gonna be taken and put into the decoder block again, and it will generate 1 token per iteration until the end of sentence token is output, and then the process will stop, and the translation is going to be completed. So some other applications for the transformers have been mainly in natural language processing. They have been state-of-the-art models lately, like language models, text translations, text summarization, chatbots, sentiment analysis. Recently, there have been some transformers also introduced into the computer vision research field. These are also competitive with the more used convolutional neural networks. And the basic idea is to transform an image into a sequence of patches, preserving also the position. In chemistry, there have been also a breakthrough late last year by Google. I think they won a competition in protein folding. They created the AlphaFold 2 model, which is also based in transformers and the attention mechanism, and they can predict they, they they predict really well proteins 3D structures from a sequence of amino acids. Another application that was done by OpenAI was DALI transformer model based on the GPT-3 model, which can create images from text prompts, like for example, an armchair in the shape of an avocado, and the model will generate these images, which I found pretty interesting. We have already like some transformer-based models in the Wolfram Neural Net repository. The BERT, Roberta, Cybert, BioBERT, and GPT-2. I might have forgot some other models, but these are available. And for example, GPT-2 can be used to generate random text that kind of makes sense, even if it's inventing what it's saying. So this is finishing. Albert Einstein was a German-born theoretical physicist who invented the electron, which is not true, but in some context, it seems plausible. Here, in this section, I added into the notebook that I shared also in Pathable. It's a toy example of a transformer for converting dates as strings in different dates formats into standard date formats. So this is, I will not go into the details, but here I trained a transformer and creating a training set using this resource function random date, and as well as yeah, the tokenization steps. And I think the idea is that it could be, you could use it as well for applying into your own problems. But since we came here to focus on multilingual translations, so Facebook late last year introduced a multilingual translation model called M2M 100, which it was trained based on mainly two large data sets called the CC matrix and CC align, which it's a large corpus of text from the web, from all kind of websites, including Wikipedia. And the key part here was to create a training set of parallel sentences from one language to another, as well as using some techniques as back translation. And what they did is to have a large transformer model that could a single model could translate between all the 100 different languages directions. So before that, the models, the multi-language models, were all converting one language into English, and then from English they were converting into another one. So they managed to create this model, which is outperforming such multi-language models. And the key idea was to add into the input sentence the language token, so the model could learn that the source sentence was in such language, as well as using as a beginning of sentence the target language token, so it would start translating the sentence into the target language. So they are using a specific model for tokenizing the sentences. This is a so-called sentence piece model, which I think Google was behind. By the way, this I think I mentioned, but the M2M 100 multilingual model was created by Facebook AI group. And the encoder, as you can see, it's using subword tokens so that a single word can be split into several subword tokens, each of these numbers. The languages also have the 100 languages that are in the model are the following ones, and I think there is even my mother tongue, which is Catalan. And basically, what I was we were doing was to create the same architecture that they use it for the model, and then we loaded the weights and bias into it. So we now have a Wolfram language version of the transformer, which is this one here, and this is the small configuration. There is another a medium-sized configuration of 5 GB, which I have not shared in the Pathable, but this one you can find it in Pathable if you want to kind of import such a large network and test some translations. And I think that they even have a super huge one of 50 GB, but the ones I converted was the small or fast configuration, and as well as the medium size 5 GB. Here we can see that there is the encoder block plus the decoder block with the different attention mechanisms. Yeah, there is the self-attention in the decoder block, and as well as the cross attention with the input coming, having the keys and the values matrices coming from the encoder the encoder stack or the encoder block. So in this case, I'm using this association for translating from English this sentence into French with using the as a start of a sequence for the decoder the French language token. And as we see once per at each step, the neural network will generate a new token. So this is not super efficient, but is since we have the full transformer, the idea to make it more efficient is to store the outputs from the encoder stack, and then so we are not computing each time the outputs of the encoder, and then also make the decoder more efficient by unfolding it. So this is the idea is that in the near future we will have this kind of net model included into the text translation function, so people can do translations with Mathematica locally, as well as the model will be into the neural function repository. And here what I'm doing is to kind of generating the text translation function using the model, and then comparing it some timings with the one that currently we have built in, which uses APIs from Microsoft and as well as Google, I think. And then a parameter that is also interesting is the beam search algorithm for decoding. And before, I think I talked about always taking the highest probability token, but if we keep a bunch of them, you can have more accurate translations by keeping several top probabilities and then combining them. So if there is some time left, here I will talk about sperm whale languages. So one of my students during the Wolfram Summer School worked on sperm whales language or communication system, since we don't really know if they have a sophisticated language yet. So sperm whales are kind of killer, are whales that are like hunting for squids and giant squids into the deep ocean. They developed this echolocation, like a sonar technology, and they have the largest brain in the mammals kingdom. And the idea is that so what researchers discover is that they produces these deep sounds during echolocation, but when they are like in the surface or like approaching surface the surface of the sea, they also communicate with each other. They have like communities of groups, and they discovered that they communicate via clicks of a few milliseconds, and they have groups of clicks that are kind of called codas, and these codas would be like the equivalent as to words as in humans. So what we did in this project was to classify the different codas by the clicks separation in the interclick intervals, and this was done in a paper in Science like a few years ago, and we use it directly the built-in classify, and we obtain really nice results. But the idea is that now that we have classifier for identifying the different codes, the idea is to try to discover some extra rules into this language, like would be maybe possible in the future if there's more data on these codes. As you can see, currently they have only like a few thousand codes recorded. The idea is to obtain a number like comparable to such large language models as that we just checked, like BERT, GPT-2, and GPT-3. And this project, the Cetacean Translation Initiative, is going to be recording for the next few years thousands of recordings of sperm whales. So in the future, we might be able to apply transformers in order to obtain like to get some insights into the grammar of their language. Actually, they discovered that they have different dialects, different communities of sperm whales. So they have kind of cultures, and we might one day using transformer models to be able to translate or understand what they are saying, or even communicate back to sperm whales. With this, I would like to thank my colleagues for helping on this project, as well as Anika Sharma, my student, who did some of the work on sperm whales. And with this, I think I will go to the question session. That's a good question. They need first to get a lot of also context information on the behavior and also identify the different individuals that they are communicating to each other. it's yeah. I guess that definitely could be useful to have a multimodal approach. And in this case, having more data, it's going to help, but there's the quality of the data should be also important. One complicated thing is that in the recordings, sometimes you have a sequence of different coders, and you don't know which coder, which whale is syncing each coder. So a good point would be to be able to separate individuals on a community. But I guess that this will come in the future years, since they just started the SETI project, I think last year or so. But I will keep an eye if they are releasing more data on sperm whales coders. So the John Castle is asking for were there any observations about the meaning that came from the classification you obtained? There were like some observations. I recall one of the coders, I think it's the 1 + 1 + 3, that they discover that it was mainly used for kind of a sort of greeting to each other, like saying good morning, good afternoon, or something like this. But for the others, it's still like unclear how they are using and how they are like communicating. And it could be that also the amplitude modulation for each individual could be relevant. So that's something that they will investigate in the future. Yeah, actually, in this SETI project, they're gonna try to create a robot. So Joseph asked if it wouldn't be more useful to actually interactively try to communicate with them. Sperm whales are not like killer whales that can be found in zoos, so it's more difficult to interact with them. But they are planning to design a robot which will produce similar clicks that they have, and then try to make them answer. No, so Dorothy is asking, will the robot be the size of a sperm whale? I don't think so. At least the prototype I saw, it was much smaller. But who knows? Maybe Steven Spielberg or is gonna design them as in Jurassic Park. But no idea on that. Yeah, I might update my notebook, and hopefully in the near future you have access to also the middle size network via the neural function repository. So if there aren't any more questions, I think I will stop sharing my screen. Thank you.